What if I told you that one day, humanity could face a catastrophic threat from outer space? A threat that could wipe out entire cities, or even bring about the end of civilization as we know it. This is not the plot of a science fiction movie. It's a scenario that scientists take very seriously, one that involves a potential collision with an asteroid. For decades, astronomers have been mapping the skies, tracking near-Earth objects, and developing plans to protect our planet from these cosmic dangers. And in 2022, NASA took a groundbreaking step toward planetary defense with the Double Asteroid Redirection Test, or DART mission. To understand the importance of the DART mission, we need to first consider the risks that asteroids pose to Earth. Asteroids are rocky remnants from the early formation of our solar system, some of which come alarmingly close to our planet. While most of these space rocks are small and burn up in Earth's atmosphere, history has shown that larger ones can cause significant damage. One of the most infamous examples is the asteroid impact that occurred around 65 million years ago, which led to the extinction of the dinosaurs. More recently, in 2013, a small asteroid exploded over Chelyabinsk, Russia, injuring over 1,500 people and causing widespread damage. This event was a stark reminder that even smaller asteroids can have a profound impact. Scientists estimate that while we have cataloged nearly all of the large, civilization-ending asteroids, many smaller, yet still dangerous asteroids remain undetected. These smaller objects, which could cause regional devastation, are much harder to track due to their size and unpredictable trajectories. To mitigate this threat, space agencies around the world are developing strategies to detect, track, and, if necessary, deflect these objects. This is where the DART mission comes in. NASA's DART mission is the first mission dedicated to testing a method of planetary defense against potentially hazardous asteroids. Launched in November 2021, DART's primary objective was to test the kinetic impactor technique, which involves sending a spacecraft to collide with an asteroid to alter its trajectory. The target for this ambitious mission was Dimorphos, a small moonlet orbiting a larger asteroid named Didymos, located approximately 6.8 million miles from Earth. The Didymos-Dimorphos system presented an ideal testing ground for several reasons. First, its proximity to Earth made it accessible for a spacecraft. Second, because Dimorphos orbits Didymos, scientists could easily measure any changes in its orbit caused by the impact. The binary nature of the system allowed for precise measurements, which are crucial for evaluating the effectiveness of the kinetic impactor technique. After its launch, the DART spacecraft embarked on a nearly year-long journey across the solar system, traveling at speeds exceeding 14,000 miles per hour. The spacecraft was equipped with a sophisticated autonomous navigation system called Small Body Maneuvering Autonomous Real-Time Navigation, SmartNav. This system allowed DART to identify and hone in on Dimorphos in the final hours before impact, a critical capability given the high-speed nature of the collision. As DART approached its target, it transmitted live images back to Earth, capturing the final moments of its journey in stunning detail. These images showed the surface of Dimorphos in high resolution, revealing a rocky, uneven terrain that would soon be forever changed. Then, on September the 26th, 2022, at 7:14 p.m. Eastern Daylight Time, DART collided with Dimorphos. The impact was a resounding success, sending a plume of debris into space and altering the moonlet's orbit around Didymos. Following the collision, scientists around the world eagerly awaited data from telescopes and observatories monitoring the Didymos-Dimorphos system. Initial results indicated that the impact had exceeded expectations. Dimorphos's orbital period around Didymos was shortened by 33 minutes, a significant change from the anticipated 7-minute reduction. This larger-than-expected result was due to a combination of the kinetic impact and the recoil effect caused by the ejection of material from Dimorphos's surface. The force of the impact displaced tons of rock and dust, which acted like a jet thruster, further altering the moonlet's trajectory. The change in orbit demonstrated that kinetic impact could be a viable method for deflecting a potentially hazardous asteroid. But why was the change so much more significant than anticipated? The answer lies in the detailed analysis of the impact and the properties of Dimorphos itself. Researchers discovered that Dimorphos is not a solid rock, but rather a rubble pile asteroid composed of loosely bound boulders and debris. This composition made it more susceptible to deformation and mass redistribution upon impact, amplifying the effects of the collision. The surface of Dimorphos, once thought to be relatively smooth, was found to be riddled with boulders and fractures. These features suggest a complex geological history, potentially involving material that was ejected from Didymos and later accumulated into a separate body. The fact that Dimorphos' surface is composed of a mix of different-sized rocks supports the idea that it was formed from debris rather than as a single solid entity. Moreover, the age difference between Didymos and Dimorphos, Didymos being around 12.5 million years old and Dimorphos only about 0.3 million years old, implies a dynamic process of formation and evolution. The debris ejected during the DART impact provided scientists with an unexpected opportunity to study the behavior of asteroid material in space. The impact created a tail of debris that stretched over 930 miles and was visible for nearly a month. Observing this debris allowed researchers to gain insights into the physical properties of asteroid surfaces and the effects of kinetic impacts. The debris tail also revealed the complexities of asteroid composition, as different materials responded differently to the impact, creating a heterogeneous plume that evolved over time. One particularly intriguing aspect of the debris was its composition and behavior. Under the influence of the Didymos-Dimorphos binary system's gravity, the plume's shape and evolution provided clues about the material's density, cohesion, and mechanical properties. The fact that the debris tail persisted for so long and stretched so far suggests that the particles were relatively fine, with low cohesion, allowing them to be easily blown away by the impact. This finding has important implications for understanding the behavior of asteroid material and how it might react in future deflection efforts. The success of the DART mission has opened the door to new possibilities in planetary defense. By demonstrating that we can alter an asteroid's trajectory through kinetic impact, we have taken a significant step toward protecting Earth from potential asteroid threats. But the mission also raised new questions and highlighted the need for further research. For example, while the kinetic impact technique worked well for a small, loosely bound asteroid like Dimorphos, it may not be as effective on larger, more solid asteroids. Future missions will need to explore different deflection strategies, such as using multiple kinetic impactors, nuclear devices, or other methods to tackle a range of asteroid types. The European Space Agency, ESA, is already planning a follow-up mission to the Didymos-Dimorphos system called Hera, set to launch in 2024. Hera will conduct a detailed survey of the impact site, map the altered terrain, and assess the internal properties of both asteroids. This mission will provide crucial data to validate the findings from DART and refine our models of asteroid behavior. Hera will also test new technologies for future asteroid exploration and deflection missions, including more advanced autonomous navigation systems and instruments capable of penetrating the surface of asteroids to study their internal structure. In addition to Hera, other missions and projects are in the works to improve our understanding of asteroid threats and enhance our ability to defend against them. NASA's Near-Earth Object Surveillance Mission, NEOSM, aims to detect and characterize a larger number of near-Earth objects, particularly those smaller than 140 meters in diameter, which could still cause regional destruction. NEOSM will complement ground-based observatories, providing a more comprehensive picture of the asteroid population and improving our ability to predict potential impact scenarios. The DART mission is not just a triumph of engineering and science. It represents a new era of international collaboration in space. Planetary defense is a global concern, as an asteroid impact could have devastating consequences for life on Earth. Recognizing this, space agencies worldwide are working together to develop and implement strategies to detect, track, and, if necessary, deflect hazardous asteroids. The cooperation between NASA and ESA on the DART and Hera missions is a prime example of this spirit of collaboration. Beyond these missions, several other initiatives are underway to enhance our planetary defense capabilities. The International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SMPAGEA, are two key organizations working to coordinate global efforts to detect and respond to asteroid threats. IAWN focuses on improving the detection and characterization of near-Earth objects, while SMPAG works on developing international protocols and procedures for deflection missions. The DART mission has also sparked interest in using alternative techniques for asteroid deflection. While the kinetic impactor method demonstrated by DART is effective for small to medium-sized asteroids, it might not be sufficient for larger or more solid bodies. One potential alternative is the gravity tractor method, which involves sending a spacecraft to fly alongside an asteroid for an extended period, using its gravitational pull to slowly alter the asteroid's trajectory. This method would require precise navigation and a long-duration mission, but could offer a more controlled means of deflection, particularly for objects that are too large or too solid for kinetic impact to be effective. Another promising technique is the use of solar sails or other forms of solar radiation pressure to gradually change an asteroid's orbit. By attaching large reflective surfaces to an asteroid or deploying sails in its vicinity, we could harness the pressure exerted by sunlight to gently push the asteroid in a desired direction. This method, like the gravity tractor, would take years or even decades to produce a noticeable effect. But it could be a viable option for slow, gradual deflections of asteroids that are detected well in advance of a potential impact. Yet another concept under consideration is the use of nuclear devices to alter an asteroid's path. While this approach is often dramatized in movies, it's not about blowing the asteroid to smithereens, which could create multiple dangerous fragments. Instead, the idea would be to detonate a nuclear device near the asteroid's surface to create a blast that nudges the asteroid off its collision course. The heat and shockwave from the explosion would vaporize part of the asteroid's surface, creating a high-speed jet of vapor that would serve to push the asteroid in the opposite direction. This method could be particularly useful for deflecting large, solid asteroids that are too massive for kinetic impact or gravity tractors to be effective. The DART mission has also underscored the importance of understanding the internal composition and structure of asteroids. While Dimorphos was found to be a rubble pile asteroid, composed of loosely bound boulders and debris, not all asteroids share this structure. Some asteroids are monolithic, consisting of a single solid piece of rock or metal, while others may have a differentiated structure with a solid core and a more porous outer layer. The effectiveness of any deflection technique will depend heavily on these internal characteristics, which are often difficult to determine from Earth-based observations alone. Future missions will need to incorporate a variety of sensors and instruments to probe the internal structure of target asteroids. Seismometers could be deployed to measure vibrations caused by impacts or other disturbances, providing clues about the asteroid's density and composition. Ground-penetrating radar could be used to map the interior of an asteroid, revealing any hidden fractures or voids. Together, these tools would provide a more complete picture of the asteroid, enabling more accurate predictions of how it would respond to a deflection attempt. The importance of understanding asteroid composition is also highlighted by the recent findings from Japan's Hayabusa 2 mission to asteroid Ryugu and NASA's OSIRIS-REx mission to asteroid Bennu. Both missions have returned samples from their target asteroids, providing scientists with a wealth of information about their composition, structure, and history. These samples have revealed that asteroids like Ryugu and Bennu are rich in organic compounds and water-bearing minerals, suggesting that they could hold clues to the early history of the solar system and the origins of life on Earth. The DART mission is just one piece of the broader puzzle of space exploration and planetary defense. As humanity continues to explore the solar system, we are likely to encounter new challenges and opportunities that will require innovative solutions. For example, as we send more spacecraft to asteroids and comets, we may discover that some objects have unexpected properties, such as rapid rotation rates, unusual shapes, or complex surface features. These discoveries could inform new strategies for asteroid deflection, or even lead to the development of entirely new technologies. Moreover, as we plan for future human missions to the Moon, Mars, and beyond, understanding and mitigating the risk posed by asteroids and other near-Earth objects will become increasingly important. Spacecraft traveling beyond Earth's orbit will be exposed to a range of hazards, including micrometeoroids, radiation, and potentially even collisions with small asteroids. Developing robust planetary defense capabilities will be essential for ensuring the safety of astronauts and the success of long-duration missions. The lessons learned from DART and other planetary defense missions will also be valuable for future efforts to utilize asteroids as resources. Many asteroids contain valuable materials, such as metals, water, and other volatiles, that could be used to support human space exploration and even establish a space-based economy. Understanding how to safely and effectively interact with these objects will be crucial for any future asteroid mining endeavors. While the technical challenges of planetary defense are formidable, there are also important ethical considerations to take into account. For example, who gets to decide whether to deflect an asteroid and by how much? While a deflection might protect one region of the Earth, it could potentially put another region at risk. International cooperation and agreement will be essential for managing these risks and ensuring that decisions are made transparently and in the best interests of all humanity. There are also questions about the potential consequences of our actions. By altering the orbits of asteroids, we are, in a sense, playing with cosmic forces that we do not fully understand. While the risks of unintended consequences are small, they are not zero. It is possible that a deflection could have unforeseen effects on the asteroid's future orbit, or even on the orbits of other objects in the solar system. These are complex issues that will require careful consideration and ongoing research. The success of the DART mission represents a significant step forward in our ability to protect our planet from asteroid impacts. But it is only the beginning. As we continue to explore the solar system and develop new technologies, we will need to remain vigilant and proactive in our efforts to detect and deflect potential threats. This will require ongoing investment in space research and exploration, as well as international collaboration and cooperation. In the coming years, we can expect to see a growing number of missions focused on planetary defense, including new observatories to detect and track near-Earth objects, new spacecraft to test and refine deflection techniques, and new initiatives to study the composition and behavior of asteroids. Each of these efforts will contribute to our understanding of the cosmos and our ability to safeguard our planet. But planetary defense is not just the responsibility of space agencies and scientists. It is a challenge that requires the engagement and support of all of us. By staying informed about the risks and opportunities, advocating for continued investment in space research, and supporting international cooperation, we can all play a role in ensuring a safe and prosperous future for our planet. As we reflect on the success of the DART mission, we are reminded of the power of human ingenuity and the importance of preparing for the unknown. The cosmos is vast and filled with mysteries, but by working together and using our knowledge and technology wisely, we can rise to any challenge that comes our way. The DART mission has shown us what is possible when we dare to reach for the stars and push the boundaries of what we know. It has given us a glimpse into a future where humanity is not just a passive observer of the universe, but an active participant in shaping its destiny. So, what do you think the future holds for planetary defense? Will we see new technologies and missions that take us even further in our quest to protect our planet? Or will we face new challenges that push us to rethink our strategies and approaches?